Hey kids, Mr. Murray here, and we're talking about functions defined as integrals. And I say that because in the textbook I use and have used a couple different places, this is called the second fundamental theorem of calculus, the second FTC as I call it. But in some textbooks, it's called the first fundamental theorem of calculus. So in any event, the math is the same, and it deals with when you have a function defined as an integral and you want to find the derivative of that function. And what's going on here is really inverse operations. That's why it's so fundamental. You know, the two major operations in calculus are derivatives and integrals. So if you take the derivative of an integral, they essentially cancel each other out. That's the big idea of inverses, right? Opposites, they cancel each other out. There is a little bit of a twist to it though. So we have f of x is the definite integral from -2 to cosine of x of 6 over 1 plus t cubed with respect to t. Notice the difference in variables here, that your integrand is in terms of t and your function is in terms of x. That's so you don't confuse the two. If you want to find f of 2, for example, you plug it in for x. But this theorem right here we're about to do, take the derivative of this. In order to do this, you really want to have a constant on the bottom of this, and that means you can ignore that basically because the derivative of a constant is 0. And what's really going to happen here is you don't have to bother to try to integrate this. That would be very difficult, first of all, because you're going to take the derivative of that integral. So it's going to basically take the integral away and leave you with this same expression with a couple important differences, that this cosine of x is going to be substituted in for t. That's what happens when you do it the long way. So I'm going right to the shortcut here, that you essentially forget about trying to integrate it. You take that away, but t is replaced by cosine of x, and then you have to multiply by the derivative of what you just plugged in, the derivative of cosine of x. So the derivative of cosine is negative sine of x, and this is because of the chain rule. And so, to clean that up, our derivative is -6 sine of x over 1 plus cosine cubed of x. And that's done. And if you know this theorem, this property, this problem is very fast. If you don't, if you sit here trying to integrate this and do all, you're going to waste a lot of time. So it's a pretty simple thing. Just remember, it's for taking the derivative of an integral. Taking the derivative of an integral. Don't bother to integrate. You're going to cancel it. But you plug in and multiply by that thing's derivative. That's it. Okay, so here is another problem and two questions based in this scenario. So just so you see the difference here, we have h of x is the definite integral from 0 to ln of x of e to the -t dt. And part A is asking you for h of 5, not the derivative, h of 5. So this means, hey, I've got h of x. It means to put x here. So h of 5 is to put 5 there. So we are going to do the definite integral from 0 to ln of 5. So I'm replacing x with 5 of e to the -t dt. And now you got to actually integrate that. That's how you're going to evaluate this and find the value of this, is by integrating. So no problem here. The antiderivative of e to the -t is e to the -t, but because of the chain rule here, that derivative is -1, you have to divide by -1 to account for that, and so that's -e to the -t from 0 to ln of 5. And plug in ln of 5 first, the top minus bottom, right? And you get -e to the ln of 5 minus -e to the -0, or just 0. And from here you can simplify a little bit. Like to get in touch with these log properties here. that this negative coefficient here, I'm going to use my log power rule and make that ln of 5 to the negative 1. So I will have negative e to the ln of 5 to the negative 1 is 1/5. And this is minus negative, so that is plus e to the 0, which is just 1. And from there, we can actually simplify a little bit further because e to the ln, those are inverse operations of each other, and they cancel each other out, leaving you with negative 1/5 plus 1. Final answer, 4/5. Very nice. So got some integration practice in there, got some log properties, but more importantly, you had a function defined as an integral, and you wanted a value on that. Hey, you plug it in and you got to integrate. In part B, however, this is where you're finding h prime of 2. So you want to plug 2 into the derivative function, which I do not have yet. So, you always make the derivative, you define the derivative first, and then you plug in any x value you might want into that. So here's our another chance to practice this second FTC, or this property of taking the derivative of an integral. Let's define what h prime of x is, right? We're not going to actually integrate this because I'm just going to plug in ln of x in place of t. So it's going to be e to the negative ln of x, but then you have to multiply by the derivative of what you just plugged in. The derivative of that upper limit, that ln of x. And the derivative of ln of x is 1 over x. Okay, so there's your h prime. So h prime of 2 would be just plugging 2 into that. So e to the negative ln of 2 times 1 over 2. And similarly, we can simplify this. Just good practice. If this were multiple choice, you would never see the answer like this. You would see it simplified. So again, the log power property there. So that's e to the ln of 1/2 times this 1/2. E to the ln of 1/2 is 1/2 times 1/2, and that's going to give you 1/4. So there's your final answer. And again, probably the easier of the two problems, but people often get a little confused with handling this derivative of an integral, substituting that in and multiplying by its derivative. Maybe they leave off that part, which is the chain rule, essentially. So there you go. Hopefully you see the difference. You can rewind and watch as many times as you like, or if you have follow-up questions, please don't hesitate to reach out and ask. Have a good day.